Inside this furnace, we've got a number of carbon steel components. They've been heated to a temperature of about 900 degrees centigrade. Now, one at a time, we're going to cool them rapidly in water. This treatment will change the properties of the steel. It's necessary in order to give the components the right properties for the job they're going to do. We call it a heat treatment process. This sequence of heating followed by rapid cooling is only one form of heat treatment. In the case of these components, its purpose is to increase the hardness of the material. Just what effect does this treatment have on the hardness of steel? Let's find out. Here's a piece of high carbon steel. We can test its hardness with a file. It's quite easy to file, so in its present state, it must be relatively soft. Now, at a temperature of about 900 degrees centigrade, we have another piece of the same material in this furnace. We'll cool it rapidly or quench it in cold water. Right, now let's see if it's any harder than the untreated piece. It's much harder. In fact, it's so hard the file hasn't cut it at all. Hardness is an essential property in many steel components. For example, the teeth round this starter ring need to be hard. They have to resist wear and indentation. Cutting tools need to be hard. They must be able to cut other materials. Now we can harden steel by heating and quenching in many different ways. These steel rollers will be used for rolling sheet steel. They need a hard surface. Let's see how this is produced. In this case, the heat is generated electrically from a ring which travels slowly up the roller. As the surface of the steel reaches the right temperature, it's quenched by a powerful spray of water. The roller rotates so that the surface is heated evenly. If we look at a specially prepared cross-section through one of these hardened rollers, you can just see the hardened area around the edge. And here's a special way of hardening gear teeth. Both sides of each tooth are heated together, this time by flames which travel slowly along the tooth. Following the flames, jets of water quench the steel. This process is repeated tooth by tooth. Now, cooling steel rapidly in cold water from a very high temperature may do more than just harden the material. If you look closely at this cold chisel, you'll find it's cracked. It may be hard, but it's no more use as a chisel. We can reduce the risk of cracking by cooling at a slightly slower rate. These steel components are similar to the ones we saw earlier in the program. Like the others, they've been heated to a temperature of 900 degrees centigrade. But instead of quenching in water, we're going to quench this lot in oil. Steel cools more slowly in oil than it does in water, and so the risk of cracking is reduced. But does the cooling rate affect the hardness in any way? Well, here we have two pieces of the same steel. We'll quench one in water and the other in oil. Now let's see how hard they are. First, we'll test the water-quenched one. This machine measures resistance to indentation, that is, the hardness of the steel. On the outer scale, the hardness is about 64 units. How does this compare with the one quenched in oil? The test is exactly the same. It appears to be softer, only 56 units this time. Quenching in oil produces a little less hardness. But can all carbon steels be hardened by heating and quenching? There's only 0.1% carbon in this piece of steel, and at the moment it's relatively soft. We've heated a similar piece of the same material to about 900 degrees centigrade. We're quenching it in water to get a fast cooling rate. Let's test for hardness again. It seems to be as soft now as it was before heating and quenching. The increase in hardness depends on the amount of carbon in the steel. With 0.1% carbon, it's hardly detectable. You need at least 0.3% carbon before steel will harden in this way. The more carbon there is, the greater the increase in hardness. But an increase in hardness isn't the only change that occurs. Here we're hardening cold chisels. They're being heated in molten lead. The lead prevents scale forming on the surface. After a period of time, the heated chisels are quenched in oil. Now the chisels are hard and will cut other materials. But watch. It's also brittle. The hardening process has left the steel extremely brittle. Now we can remove brittleness by further heat treatment. It's a process known as tempering. The chisel is heated to a much lower temperature than that used for hardening. In this case, about 280 degrees centigrade. The chisel is held at this temperature for about 2 hours. The surface of this chisel has been polished and at this temperature appears purple in color. We now quench in oil. This time we have a chisel that's hard enough to cut, but not so brittle that it breaks. Tempering has removed some of the brittleness, which of course makes it tougher. In engineering, we rarely need steel in a very hard and brittle condition. These components have just been hardened. Now they're going to be tempered. In this case, we're not dealing with cutting tools. They are, in fact, axle housings. For this job, they don't need to be quite so hard as the chisel, but they do need to be tough. To achieve this, they're going to be tempered at a much higher temperature. Once sealed, the furnace will be taken up from here to 550 degrees centigrade. At this temperature, we'll not only remove the brittleness, we'll also remove some of the hardness. Now here's something for you to think about. This chisel has been very carefully hardened and tempered. But in resharpening the chisel, this chap is pressing so hard the point is getting red hot. What do you think this will do to the hardness of the cutting edge? Here we're cold rolling mild steel strip. It's a process which reduces the thickness of the steel. In this process, the steel is passed between two large rollers. Let's look at the principle of rolling in a diagram. Here, the steel is going from right to left. In the middle are the rollers. As the steel goes through the gap between them, its thickness is reduced. Deforming steel, when it's cold like this, is known as cold working. In one pass, the thickness is reduced by only a very small amount. So now the rolling direction is reversed, the gap between the rollers reduced, and the process is repeated all over again. Each time the steel is rolled, it's being cold worked. But cold working changes the mechanical properties of many materials, including steel. If we bend a piece of cold worked steel, this is the result. It's lost its ductility and it's become very hard. Now, in many manufacturing processes, we need to be able to bend sheet steel. The body panels of cars are made by pressing out sheet steel in a huge hydraulic press. For this process, the steel needs to be relatively soft and ductile. So, after cold rolling, the properties of the steel must be changed. We do this by heat treatment. It's a process known as annealing. Here, several coils of cold-rolled steel are going to be annealed at the same time. Now, when steel is heated in air to a high temperature, a black oxide forms on the surface. To prevent that from happening, these coils are enclosed in a special jacket. Before heating, the air trapped inside the jacket will be replaced by a gas which does not cause oxidation. That's it. Next, the jacket is enclosed in a huge furnace. Steel is annealed first by heating it to a high temperature, just as in hardening. In this particular case, the temperature is set for 680 degrees centigrade. This temperature is held for a specified time, and then the steel is allowed to cool in the furnace. This means the cooling rate is very slow indeed, quite the opposite to hardening. Now, what happens if we try bending a similar piece of annealed steel? It bends without fracturing. By heating and slow cooling, we've restored the ductility and made it softer. Many engineering processes involve cold working a material. Here we're drawing copper tubes. This reduces both the diameter of the tube and the thickness of its wall. In turn, this has the effect of making the tube much longer. That was only one of a sequence of draws needed to get the tube down to the required size. Each draw involves quite a lot of cold working, so you can probably imagine what's going to happen here. To prevent this from happening, we must change the properties of the copper by annealing. This involves heating them in a furnace to a fairly high temperature. For copper, about 650 degrees centigrade. Again, this furnace has been filled with a special gas to prevent oxidization. In the case of copper, we don't have to leave the material to cool in the furnace. It can be cooled quite quickly with water. Annealing has increased the ductility of the copper and reduced its hardness. Now it can be bent without fracturing. However, for many practical applications, this tube is too soft and too ductile. So it's given one final light draw. This will result in a tube that's not too hard and not too ductile. Here's a situation where toughness is an important property. The large steel links used in lifting gear are often made by forging. This can leave the material in a stressed condition, with properties unsuitable for the job it has to do. These stresses can be relieved by another heat treatment process known as normalizing. Again, the steel must be heated to a fairly high temperature. These rings will be left in the furnace for about 2 hours at a temperature of about 900 degrees centigrade. When time is up, the rings are taken out of the furnace and left to cool, this time in air. This not only relieves any stresses in the steel, it also increases the toughness of the steel. Let's compare the toughness of a piece of forged steel before and after normalizing. Here's a piece of forged steel that's been specially prepared for the test. Now, toughness is the ability of a material to withstand shock loading or impact. That had a toughness value of 25 units. Now for the normalized piece of steel. For comparison, the test must be exactly the same. That had a toughness value of about 30 units. Normalizing has increased the toughness of the steel. Heat treatment is one of the most important methods of getting the right properties, especially in steel.